Hey Martin, how are you doing?
Good evening, sir.
Oh, there you are. We were just looking for you, Martin. Thank you.
Trying to navigate the system.
All right, I think we can get started. We have all the things set. So Dhruv, can you confirm that my screen is visible?
Yes, it is.
Yes, your screen is visible.
Okay, thank you. So hello everyone and welcome to the third day of Connections 2022. This is a hot in networking topics track today, and the Connections 2022 is being brought by IIE SOC and INTC. It's a post-IETF 113 forum. We have a wonderful set of speakers today. We have Martin with us, we have Adrian, and we have Dirk. So let's get started without waiting further. First of all, we would like to thank all our sponsors. We'd like to thank Cisco. We'd like to thank the Internet Society, APNIC Foundation, and Juniper Networks for supporting Connections 2022. We really appreciate the kind support that you have provided us to go ahead with this particular event. I would like to request Kathy here. I would like to invite Kathy to please give a brief introduction to Scott Bradner, and then we'll go ahead with a special video from him. Over to you, Kathy.
Hi, everybody. So we asked, this is our continuing series, we asked members of the community what keeps them up at night with respect to the internet. And this message is from Scott Bradner. Scott's a long time volunteer on the internet. He's had a number of really managerial leadership roles in the IETF. Until his retirement in 2016, he was the University Technology Security Officer at Harvard University. He's talking about some routing stuff that didn't used to keep him up at night, but now it does. So let's hear from Scott.
Thanks, Kathy. I'll just play the video.
What keeps me up at night regarding the internet? Well, I'll start with something that has not kept me up at night, at least until very recently. For a very long time, in internet years anyway, the powers that be have been warning us that the internet BGP routing system was super fragile and could collapse or be corrupted at any time. I recall Richard Clark, the first US cybersecurity czar, saying that in about 2002 and pushing for the IETF to fix the vulnerabilities. But this threat doesn't keep me up at night because time and time again, ISP geeks have quickly discovered routing issues and have fixed them. And I expect that to continue. But in late February, the US Federal Communications Commission, the FCC, started a study of BGP vulnerabilities with the aim to find out what steps the FCC could take to protect the internet infrastructure from BGP vulnerabilities. I'm worried that the FCC will develop regulations they say will make things safer, but in fact will be an inflexible set of rules that actually makes the US internet more brittle and are a continuation of the FCC's long history of not understanding how the internet actually works. A little bit of history. The first international treaty on telecommunications, the 1865 International Telegraph Convention, included a requirement that telephone companies be able to block any communication that, quote, would appear to endanger the security of the state or would be violating the laws of the country, the public order, or moral standards and values, end of quote. For many reasons, the internet in general has escaped most regulations of this type for most of its history. But over the last decade or so, the efforts of grandstanding politicians and governments to apply the 1865 requirement to the internet, creating clones of the Great Firewall to protect the security of the state by as the government official, non-US government official once told me, blocking information that would confuse the citizens. That is information that was in some way different than what the government was saying. And also creating laws to, quote, protect the children, end of quote, which usually means laws that would destroy the open forum, that the internet has been a forum that has been both good and bad. These politicians seem to be a worldwide phenomenon. thinking about these efforts is not sleep-inducing.
Right. So thanks to Scott for that. Okay, let's move on. Just a few things for the audience participation today. We have an excellent set of speakers for the sessions today. It would be amazing if we could get questions from all the participants. So please ask questions. We have a Q&A in Zoom where you can put your question, and you can also use chat for other kind of discussions that you would like to have. Putting the questions in Q&A will ensure that all the questions are visible, and the other audience can also kind of upvote questions. It's important. We have, if you look at the last point in this particular slide, a very interesting thing. We will identify the best person, the person with the best question for the day, and we would make a donation to their recommended charity and cause. So please do not hesitate to ask any questions. We look forward to a very interactive session today with our speakers. So getting started with our first speaker, Martin. Thank you, Martin, for joining us. Martin Thomson enjoys making protocols. He takes particular pride in making protocols that lots of people use, like HTTP2, Quick, and Web Push. Making protocols that are safer, more secure, and private is his particular focus. Martin is a distinguished engineer at Mozilla. Thanks, Martin, for joining us. I would now allow you to share the screen. Yes, we can see your slides.
I will see if this is going to do the whole presentation thing. Look at that. It's like magic. I don't know how much of this is in the way of the what's on screen here, so I'll do my best to make it go away. This is really quite difficult. Okay. Thanks for the introduction. Right, that pretty much covers everything. I'm going to take opportunity to talk a little bit about some work that's relatively new in the IETF. We're talking a little bit more recently about this notion that there's IP address privacy is something of a risk to people. And proxying in general has been an approach that has been used in a number of cases, and VPNs in particular, quite widely used. But we find that there's a number of limitations with those. And what we're looking at here is something that's much more lightweight. And we call it oblivious HTTP. That's what it's called currently. And I suspect by the end of this, you'll know a lot more about how it works. So, the problem. This might go back to Scott Bradner's point about people using services without other services knowing who they are. So, we have a lot of client-server interaction protocols that kind of look like what you see in the diagram here. Clients make requests and servers provide responses. Pretty straightforward. But it turns out that providing this sort of service can expose the servers to information about their clients that perhaps they wouldn't want to know. Things like what the content of the request is, but also who's making the request. And in a lot of cases, we don't tend to care particularly much about this sort of small leakage of information towards servers. In fact, as many will observe, a large amount of the web in particular is sort of grounded in this small release of information to servers. They collect it all up and build profiles on people and then sell that. So a lot of servers don't particularly mind this sort of thing, but over time there's a lot of information that clients sort of inadvertently share with servers. Take an example. DNS. So when you make a DNS query, you have to tell the DNS resolver that you're talking to what domain name you're interested in. And a DNS resolver over the course of days and months and weeks that you're using it will reveal quite a bit about the names that you've been interested in. And so you can sort of imagine that over time the resolver can build up something of an interesting picture of you just based on the information that you're giving it. This, of course, concerns a number of people and looking to find ways to improve the situation. So kind of at its core, there's a number of problems here. One of the major problems that we find is that privacy might become unacceptable if the requests are attributed to you as a person. And this can mean a number of different things. We could authenticate you. We could actually know your email address or your actual name. In a lot of cases, when you're surfing the web, there's cookies that are attached to you, and there's sort of a pseudonymous identifier that sort of the website sticks with you, and then it sort of tracks you around over the web. And then there's all of the network identifier stuff, and this is where the networking side of things comes in. You release your IP address to a website when you make a request from it. And if you think about building a privacy preserving system that serves DNS, for example, you might be able to avoid some of this, but you can't avoid being exposed to things like network identifiers. And this is where intermediation comes in. The privacy problem also comes down to correlation. And if you think about the small release of information, maybe that's not so bad. But over time, as the profile of names that you're querying sort of get built up on the server, then it can correlate them all with the same person. And that can build up to be quite a lot of information. And what you end up with is this pseudonymous attribution. You don't necessarily know who this is, but there is a person with the following properties making these requests. And correlation is often a side effect of some of the things that we do to make the network work better. Performance improvements like connection reuse and TLS session resumption and zero RTT are things that we use to make things go faster, but ultimately they end up connecting activity together over time. So back in the long, dark history of my interactions with the IETF, I worked in geolocation. And this is a particularly interesting area for this because it's one of those things that people don't always realize just how much information they're releasing when they provide geolocation relevant information. And so if you think of an example where you've got a mapping service, you're going to OpenStreetMaps, for example, and you want to see a particular part of the map. And so you retrieve tiles of a map that surround the area that you're interested in. But what tiles you retrieve reveals maybe your location or maybe the location you're interested in. And over time, particularly when it's tied to your location, you can build up a profile of your movements. And then it turns out that there are examples like the one here on the slide where that information can be used to de-anonymize people. So you have an anonymous, pseudonymous data set that has these profiles of where people have been, but that information can be used to find out information that perhaps you might not want to have revealed about you. As a service, maybe you don't want to have that information available to you either. So the basic technique that we use here is intermediation to hide network addresses from servers, to provide this extra layer of privacy for people who are making these queries. That allows the ultimate network address, the address that it's attached to the client, to be hidden from the server. And so the server only really sees the network address of the proxy, and presumably if there's a lot of people using the same proxy, all those people then effectively become indistinguishable from each other, and the server has no way to distinguish between one particular person or another. And then, of course, we use encryption so that the proxy can't look at the messages that are going back and forth. So you have an arrangement where the proxy knows about the network location of the client, so it can deliver the responses to them, but the server knows the contents of the request, but the two of them together can't join those things together. So there's a lot of connection-based proxying systems out there. We have sort of HTTP level proxying. There's work in the IETF now on mask, which is taking that sort of HTTP level proxying up to the next level and being able to do more advanced networking, add more advanced networking capabilities to that. There's all of the VPNs. People might be familiar with WireGuard. All of these things essentially provide you with a remote network interface somewhere else in the network. And if you're talking about making connections to servers, you essentially have to make TLS connections to servers, and that takes time. And so people tend to do things like reuse connections, just as you would when you don't care about the privacy properties. That improves performance, but when you start reusing connections, then you start enabling correlation, even when you're running through a VPN or something like that. That's okay for a lot of applications. Maybe you're viewing online video and you're authenticating to access that video. Correlation doesn't really bother you in that case, but not always. DNS and mapping examples are good cases that you might imagine that having correlation is not so good. The performance of this make a new connection is not particularly good, and this slide sort of shows the absolute best case scenario of I want to make a request via a proxy. How long does it take? And there's a lot of performance optimizations kind of implicit in this, but you sort of layer in your creation of a tunnel, opening of a TCP connection, creating a TLS session, you overlay all those together, and that still takes a round trip. And only then can you start sending off another request. And if you have the fastest proxy in the world with all of the optimizations enabled, you might be able to do 2 round trips to make a request. And then, of course, if you wanted to break the connection, the correlation between that request and the next one, that's another 2 round trips. Also, it's pretty expensive in terms of the communication overheads and cryptographic overheads and things like that. So Oblivious HTTP sort of slims this down a great deal. It uses message level encryption, which is not especially new idea. This is something that we considered actually well before my time in the 90s. There was a long discussion about doing message level encryption for HTTP rather than what we understand today with TLS. But now we have some more modern tools for doing these things, and it turns out to be a relatively straightforward protocol. You have this hybrid public key encryption. The server publishes its public key, and then whenever the client wishes to make a request, it encrypts a message toward the server, sends it to the proxy forwards it to the server, and the server can respond via the proxy. 1 round trip. So aside from that 1 round trip advantage, there's relatively low overheads for this. So there's a modest size increase in terms of the size of the messages that you're sending. And there's a relatively small amount of computational overhead for doing the hybrid public key encryption that's used. And the advantage then is that you can make requests with no network identifiers attached to them, and the requests are uncorrelated. The limitations, however, are probably worth pointing out. Privacy here depends on the server providing only 1 public key to everyone. If clients were given a unique key, then they would be able to be tracked. And so there's a bunch of interesting techniques that you might need to deploy in order to ensure that this is the case, particularly if you're a client and you don't entirely trust that the server is treating you fairly. So there's a document there that talks about those sorts of things. Probably the more interesting one is replay attacks. This is not something that you necessarily want to be able to use on a general purpose request response protocol. Because although the proxy can't read the messages, it can capture them and send them to the server again later, or simply delay them. This could be bad if the request has some sort of effect, particularly if that effect, when repeated, has consequences. The classic example is, please transfer some amount of money to this account. You repeat that one, and suddenly you're doing twice as much, sending twice as much money, or 10 times or 100 times as much. This probably isn't so much of a concern, because we also expect that the request will be anonymized and be used for things where there's no authorization attached to the message. There's some other interesting requests on privacy. In the DNS example, talking to a DNS resolver, the resolver will often cache the thing that you requested of it. And so when you come back to the server again, it will serve that response out of a cache. It allows it to make the response faster and scales very well. But of course, if the proxy captures a request and replays it, then it can observe the state of the cache based on, it can observe the effect on the cache based on the time that it takes for the resolver to provide an answer. And so longer time, probably not cached. Shorter time, maybe that was cached. And then it can make some inferences about what it is that the request contained based on other things that it might be able to do, like make its own queries to the resolver. So these are things that you need to be aware of. So there are some basic tricks you can use for anti-replay. There's a bunch of discussion about this at the moment, but simple one is you just remember the requests that you've had, and you remember them for a short period of time. And if the time is outside of that window, you throw them away. Pretty straightforward sort of tricks. Of course, there are other interesting operational problems to consider here. One of the primary techniques that denial of service risk uses to manage, that the services used to manage denial of service risk is the reputation of IP addresses. And so if you're operating a service and you don't get to see people's IP addresses, suddenly you have some interesting problems, of course. It's very difficult to operate a service when you're unable to defend against denial of service attacks, particularly given increased prevalence and volume. So the basic answer here is that the proxy needs to provide denial of service defenses, and the server needs to trust that the proxy is going to do this. There may be some opportunities for the two to collaborate, such as if the proxy detects that a client is maybe attacking it, it might be able to pass information to the server. And this may be a privacy risk, so the client will need to know what sort of information will be passed along. It won't necessarily know whether the flag is on, but the proxy could say, hey, this particular request comes from someone who looks a bit suspicious, and then the server can take an action by sort of slowing that request response down or something along those lines. This part is very much still under discussion at the moment in the IETF, and we haven't quite gotten to the bottom of exactly how we're going to manage these signaling things, because of course, once you start providing signals like this, it allows the server to divide the population of clients into multiple groups and reduce the privacy advantages that we're gaining. So in summary, the proxy needs to be trusted both by the client to not reveal its identity to the server, and by the server to not facilitate denial of service attacks. So with all of those caveats in mind, the basic premise here is that if you have a request response exchange where you're looking for reasonably good performance, particularly performance in terms of latency, and the requests that you're talking about have some sort of sensitive information that's only modestly sensitive when attributed to a client, and you want to hide network addresses from servers, then this is potentially something that would be interesting to be used. You also want to make sure that you don't need stronger privacy protections, and there are much more robust protocols for things. This is essentially a very, very lightweight version of onion routing, for example, and Tor provides a far more robust system for anonymity. And then, of course, if you're interested in providing true guarantees about the privacy of the information that the server is handling from the clients, then multi-party compute systems are also an option, and the IETF is talking about those in PPM. And that's all I have. So I'll open this up to Q&A. I might drop the slides so I can see who's making requests.
Yeah. We have one question. I can read it out for you.
Sure.
Doesn't the proxy also need to be impervious to government inquiry?
This is an interesting question. It depends on your threat model. So I think Tony is probably jumping to a particular threat model here, and I'm not sure exactly what answer we're talking about. The trick here is that if the server is vulnerable to the type of attack that I think Tony's talking about, is where the government has the subpoena or sends the police around to ask for the information, or gets a warrant or something along those lines. The server logs will not reveal the identity of the person who's making the query. And so in that case, yes, the client's anonymity is somewhat protected, but the information could be correlated with information in the proxy if the proxy also retains information. And so it's going to come down to client judgment and the circumstances involved and the threat model as to whether you care about that sort of thing. All right. I see.
We have a question from Barbara as well as Adrian. So let me go ahead with question first from Barbara. Yeah, it's in the chat box, just in case you would like to see. So it says, how does an enterprise small business home network monitor for detect malware inside the network that is using this mechanism to keep its nefarious activities private? And how do they prevent inside the networks that own from using this to bypass the network policy?
No, this is a classic question. This is just a variation on a question that I often receive. So encryption is often can be used to exfiltrate information from networks, particularly by malware and bad actors. This doesn't really change that. This provides honest clients with the ability to access these privacy properties that we're talking about here. Of course, malware can already do these sorts of encryption things in order to evade things. The question, I guess, really comes down to whether that is detectable, and that's an ongoing debate, I think we'll have to say.
Mm-hmm. Okay, we have, okay, so Barbara, do you want to add something to this? Maybe you can unmute and say.
No. Good.
Okay, all right, we have answered. Okay, so let's move to the next question, and then we can go to Mike as well. Mike's hand is up, so let me first take this question from Adrian. The question from Martin is that, is this approach currently limited to HTTP? Would you see us moving more client-server protocols to run over HTTP, or extend this approach to each other's transport?
So I think this sort of cuts both ways. I mean, obviously we're seeing DNS over HTTPS be introduced and become somewhat successful, and that's an example of taking a protocol and putting it over HTTP. I don't think from an architectural perspective that's the ideal solution. I think it was an expedient solution for some of those involved. The DNS over HTTP, DNS over TLS, or the more recent DNS over QUIC are probably more appropriate protocols to be running for most clients in that setting. The draft that we're talking about here, the Oblivious HTTP draft, does talk about taking the general framework that we're using here and applying it to different protocols or different payloads. And so you could carry something other than HTTP within HTTP this way, or you could use this to carry other protocols inside an arbitrary protocol. We're currently just defining this for using HTTP to carry HTTP, but it could be very easily extended.
So Adrian, do you want to add something to this?
Yeah, thank you, Martin. That helps a lot. And what I'm thinking about is how this ends up in software stacks for general availability, which obviously, if everything runs over HTTPS, then well, we get it for free. But if we go on using a variety of transports and each of those has a variety of implementations, then getting this out into the field becomes hard.
Yeah, so it turns out that there's not a huge amount of code required to do this. I think it's only, I couldn't say offhand, I have the implementation sitting there, it's like 100 lines of code tops. The main bulk of the work is in the HPKE work. So the general framework that we have here can be easily applied elsewhere without too much extra work. And I'd expect that we'll look at doing that now.
Okay, so let's move to Mike. Mike, you want to go ahead with the question? And then we'll come back to a couple of questions that we have in the chat and then go to Thiru. Mike?
Thank you, and thank you, Martin. This is fascinating stuff. We at Enterprises use a lot of proxies, and probably more to come in the future. And you've warned us about a few things there. And should we be looking to reduce the number of proxies in the future? Is there a better solution looming on the horizon? And I hate to throw this in there, but how does NAT fit into your proxy scenarios? Is that better or worse, or does my question make sense?
Yeah, so I think there's probably a number of questions hiding under there. I'll address the NAT one quickly. This all sort of, at least for the HTTP scenario, to Adrian's point, operates at a level much higher than that. And so the expectation is that we wouldn't be particularly affected by presence or absence of NATs. The more interesting question, I think, is the implications for enterprise. And that sort of, I suspect the use of proxies in enterprise is often so that various monitoring services can be enacted. So you ensure that when people make requests via a proxy, the client endpoints are configured with trust anchors so that proxy can intercept communications outbound, inbound, in order to apply policies, we'll say. And so in those settings, the question that you would naturally have, and I think this runs on from Barbara's question as well, is, well, is this going to be used in a way that would make it difficult to do that sort of monitoring? And that's really a question for the specific deployments that we're talking about. So if you look at the deployment that we're considering for using this for DNS resolution queries, the expectation that we have is that when there's interception set up in that way, we would probably disable the features that rely on this as well. And so an enterprise that was relying on interception capabilities wouldn't wouldn't be affected by the deployment of this, whereas most of the people outside the enterprise would be able to use these capabilities and get the privacy advantages. In terms of what proxies, what enterprises might do or not do with proxies, I think that's a much bigger discussion, and I can't really speculate too much on that.
Okay, thank you very much.
Thanks, Mike. Thanks, Martin. We have one question in the chat box. We can take that first, and then we can go to Thiru. The question in the chat box is from Vimal. How HTTP services can be scaled over blockchain?
Oh, that's a difficult one. I'm not sure that I have a good answer to that one, because I'm not even sure that I understand it. Perhaps the person requesting this can try to clarify the question. I can get back to that.
Yeah, sure. So, Vimal, you can let us know whether you would like to just provide a little more details on the question. Can raise your hand and then we can, yeah, okay. So I see him. Yeah, so you should be able to unmute and talk, Vimal.
Thank you, Martin, for your wonderful insights on HTTP services. Actually, I am nowadays working on blockchain, which is based on purely on peer-to-peer networks and peer-to-peer systems. So since HTTP has the client and server components, which is basically, does not suit to the blockchain environment. So I am having this confusion that how purely in a purely blockchain environment, in a decentralized environment, how this client, centralized HTTP services will be scaled over. So that is my confusion, if you can clarify it.
Yeah, so the peer-to-peer scenarios are something that came up continually while we're working on Quick. And something like this does generally have applicability in those peer-to-peer scenarios if you consider the possibility of routing queries for your peers. Say you have a DHT or a system like you're talking about. If you route your request via some other party within that network, you can use this to, for instance, obscure the IP address that you're using. But that would require some amount of cooperation from the network. I don't know enough about those systems to be really able to opine on the suitability of something like this. But it certainly could be adapted to run in a peer-to-peer environment.
Yeah, thank you very much, Martin, for your response. Really quick, maybe useful in that scenario. So I'll definitely try to explore the things about how Quick can be useful in that scenario. Thank you so much.
Right. Thanks, Vimal. Thiru, maybe you can go next.
Hey, Martin. My question was with enterprises and homes migrating to provide encrypted resolvers, right? How is this going to be? Is it more going to be like an opt-in where the user opts in to use this and doesn't use the network provided resolvers? Or is it going to be like by default, you're going to ignore DNR and DDR and just try obvious HTTP because it gives better privacy? How do you see an average user getting to use this? Let's say I'm walking into a coffee shop and I want to use obvious HTTP, but I'm sitting at my home and I know I'm getting my home network offering me security, and I still want to use my DNS server to doing that, right? So how does an average end user go doing all this toggling, right? Is there a better way to make this more visible to end users to give better privacy in networks where he really wants obvious HTTP, but not in the other, right? Yeah,
so there's a bunch of deployment level questions here that I think are really interesting, and I know we're having those discussions in the OI working group and as well the I think it's ADD as well. Aren't you on a draft that has some discovery components?
Yes, and I wanted to hear your opinion on that because you're mostly on the opposite side of the fence. And
Not necessarily. I think there's a lot of value in the DNR, DDR work for discovery there, particularly in those settings where you have a variety of policies. So you have networks with a particular set of policies, and you have endpoints with a particular set of policies, and simply providing the information that these sort of discovery systems provide allows the endpoints to sort of synthesize that into some sort of action. I can't really speak too much about what our plans are in terms of Mozilla and Firefox and what have you. I can only really say that our expectation is that we're working with partners who provide the DNS resolver components, and we're also looking at other partners who would provide a proxying service. And so for most people with no DNR, DDR discovery mechanisms for these things, we would probably look to have some sort of default setup that uses something like oblivious HTTP in order to get the privacy advantages. And then the question then becomes, well, if there is a local service, under what conditions would we use that service? And that's probably something that needs to be worked out. It's quite likely we would try to use the local resolver, but with a pre-configured proxy that we've chosen. And I think that's along the lines of the draft that you and Tommy Pauly from Apple have worked on. But there's a lot of interesting and tricky questions that need to be answered in order to get to that point because of the trust relationships that I talked about.
Right. Thanks, Martin.
Thanks, Thiru. So there is a note, I guess, from Dirk. I think this is more related to what discussion we were having with Vimal. So I think Vimal can take a look at this note. And Martin, do you want to add something to this? I don't see this as a question. This is just a note from Dirk.
No, that's good information, but I don't think we need to comment on it.
Okay. Yes. So we do have a few more minutes. So if somebody has any questions, you can put it in the Q&A, or you can raise your hand, and then we can allow you to unmute and then discuss with Martin.
Yeah, I have a follow-up question. I mean, if there are no questions, I can take.
Sure.
So Martin, I've read the key consistency. That seems to be one major problem with regard to this, right? And the protocols that being worked at MASK or HTTP Connect, they could be the ways for the client to discover the keys through a proxy in that way that the server doesn't identify that, right? But I saw that draft is mostly informational, and I don't see any concrete proposal on what would be the implementations that would pick in a more generic way and not leave it to various level of interpretations on consensus and all, right? I mean, consensus is more like, hey, I will have clients revealing it in a blockchain and all of that. I mean, those seems like some of the techniques are quite complicated. I don't know how it's feasible to implement, but any technique which is like using a proxy, for example, to discover these, using DNSSEC, right, with a large TTL value. So something like that would be a reasonable approach that I thought would be to implement and get this going forward without having about key consistency. Any thoughts on that?
Yeah, so there is a very much simpler answer to the key consistency question. It's not a particularly good answer in terms of scalability or open access to things. It certainly tends to centralize things, which is one of the key sort of criticisms that's been leveled at some of these things. But ultimately, I think we're at the stage where we're just learning, and just having clients configured with a key for a server is very much less open to abuse and very much simpler than a lot of the other options that we've got in that document. That document sort of considers the full spectrum of things that you might do, and of course there's a bunch of things there are probably impractical, like you say, putting things in Merkle trees or trying to replicate the certificate transparency system or something along those lines is rather expensive. But I think we can probably work on better solutions, and it will depend on the protocol and the deployment and the type of clients and a number of other factors that we can't really say just yet.
Okay. Any follow-up, Thiru?
No, that's good.
Okay. All right.
Brilliant. Thanks, everyone.
Yeah. So Yeah, thanks, Martin. Thank you for this very interesting talk, like Drew has already mentioned. And more importantly, thank you for staying up so late for us to have this particular session. We are very grateful to you. Thank you so much. Yeah. All right, so moving forward with our sessions. So I will start sharing the screen. Give me a minute. Okay. So we are ready to go ahead with our second speaker for the day. We have Adrian with us, who is going to talk on semantic routing, challenges and benefits of routing on more than just addresses. Let me give a brief introduction to Adrian's profile. Adrian has been at the forefront of technology innovation in ITF for nearly 25 years and has co-authored more than 85 RFCs specifying internet technology. He was part of the effort that developed MPLS and was one of the pioneers of generalized MPLS and the path computation element, PCE. Within the ITF, Adrian has co-chaired a number of working groups and served as one of the 2 ITF routing area directors for 6 years. He's currently the technical advisor to the ITF's TEAS working group and has just reached the end of a 4-year term as the independent submissions RFC editor. Adrian has written, edited, or contributed to 9 books on internet technologies, which includes the internet and its protocols and the GMPLS architecture and applications. And he has also authored 4 volumes of fairy stories for adults of all ages. He runs a successful consulting company, Old Dog Consulting, specializing in internet protocols, SDN and NFV. Thank you so much for Adrian for joining us today. I'll stop sharing the screen and you can start sharing the screen. I can confirm.
Thank you, Drew, Martin, and Mohit. I'm just waiting for this thing to share. There we go. Yeah, I'm going to try and talk a little bit about routing. And I just spent some time flicking through the attendees and discovered there are people here who know more about routing than I do. So it's going to be an interesting talk, in particular because I want to bring everyone up to the same level. So there'll be some background here as well. And listening to Martin made me realize there's one thing I should have said more clearly in my slides, and that is I'm talking about packet routing. So not determining where to put transport paths or which servers to attach to or how to route client server requests, but actually routing the packets in the good old way that we always used to. So a lot to talk about, and I will probably run through some of this really fast. So a quick reminder of what routing and forwarding is, and then introduce the concept of routing beyond reachability. So routing on more than just an address. Then we'll look at how to add semantics to packets to guide the routing and forwarding, some existing approaches and new proposals. That'll be a really quick run around because there are very, very many of them and we couldn't possibly cover them all. And then the thing I really want to get to is the discussion of the challenges, the architectures and the risks, and taking that on to how do we actually do routing research and what should we be aware of. So a quick forwarding is not routing 101. You all know this, but it's really important. Forwarding is when the packet arrives into the router and the router decides where to send it. Usually does this using a lookup table. And this is a local action. Routing, on the other hand, is about determining what information goes into these lookup forwarding tables, running an algorithm based on the information that is known about the network, and some objective criteria, such as shortest path first. And routing is a network-wide action. So just to confuse things, we also talk about routing, meaning routing protocols. And these are the protocols that distribute the information, typically the topology and state information that's used by the algorithms. And we can run these algorithms either centrally or at each router. If it's central, then we have to use some kind of controller to program the forwarding tables and push the information down into the network. If it's distributed, then we can enhance it by pushing static routes configured by the operator into just individual routers in the network. So the really quick background to routing is based on Dijkstra and his algorithm for computing shortest path first. And this quickly leads us to add metrics or link lengths or link costs to every hop in the network, and SPF becomes least cost. That metric may be related to distance or money or reliability or anything you want, but it needs to have a common meaning across the whole network. And there are ways in IP networks to look at the traffic flows and tweak the metrics in the network in order to change how the routing algorithms will actually program the forwarding and achieve some form of traffic engineering and load balancing. So Dijkstra's algorithm is embedded in the definition of OSPF and ISIS so that all the nodes in the network make the same forwarding assumptions. And this is pretty important because if you do something different, then you may build loops in your network, or you may have traffic that just disappears and never reaches its destination. And wonderfully, SPF is really actually quick to compute, even in very large networks. So in terms of router forwarding behavior, routers don't simply take packets from one interface and send them out of another. They have to queue the packets, definitely on the output interface and often on the input interface, because they have to be resilient against congestion. So for example, if two packets arrive on different interfaces at the same time and are forwarded out of the same interface, one of them has to go first. So there's some queuing. And we can influence the forwarding behavior in a router by saying which queues will get processed first, which packets will get dropped if queues are full. So this prioritization usually depends on marking the packets so that we know which ones get better treatment. And examples really are from diffserv in IPv4, the type of service, in IPv6, the traffic class, and in MPLS, also the TC bits. Additionally, there's sometimes parallel links between routers, and they have the same cost. So the forwarder needs to be told how to send traffic to load balance across those links to get the best use out of the network. And a key thing there is that we want all packets from the same flow to go across the same link so that we avoid any risks of reordering. So ECMP and various evolutions of that, like weighted ECMP, is resolved by looking in the packet for well-known fields, and the old style was to use source, destination, next protocol, and the two ports, and to hash these, and then the packet could be given to an output interface depending on the result of that hash. There are ways of pre-hashing and putting the result in the IPv6 flow label or the entropy label. So what is extra? What can we do beyond simply routing on the best path to the destination? So the evolution that's going on here is about improving what the internet can do, dealing with more complicated deployments and looking to the new uses and applications that are coming along and what they require or expect from the network. And what's going on here is that we run more complex routing algorithms to determine a set of paths, and then we can use those paths for different purposes. And those may be different path qualities or independent protection. And as we do that, we take into account more information. That information may be the capabilities of the network or the state of the network and the desires of the traffic source as expressed in information carried in the packet. So what are these different routes and why do we have them? I think the way to say this is that the shortest path is not always the best path. And a really well-known instance of this is traffic engineering, where we're trying to steer the traffic into different paths depending on the link capabilities, the current use of the network, and maybe to provide protection paths. But big question is, what if we want to create different paths for different network behaviors? Maybe one path is high cost, but has super reliable delivery. And another one has low latency, but maybe it's also got low bandwidth, and so on. So we have this concept of different paths for different qualities. And what we're really doing is defining the meaning of best depending on our application. So how do we influence the algorithms? How do we get different paths computed in order to program our forwarding? Across all of this, we must remember that we need to get consistent results across the network. It's no good having one router in the network being really clever and computing smart paths, but all of the other routers are doing something different, because the traffic will bounce around. The packets will get onto loops or will get lost. So we could set this out as just saying the algorithms that everyone implements must have the same objectives. And that should be enough, but well, I think we've kind of seen bugs in the past, so it's better to have identical algorithms. Those algorithms are aware of the topology and the state in the network, and they could just be really simple, like SPF or CSPF, or they could be complex, using lots of different information and actively changing outcomes as that information changes. They can be distributed, as we've already mentioned, or they could be centralized and used in an SDN sort of way. Right, and then I wrote this title, How Routes Get into Forwarding Tables, and then realized, well, we keep getting running into this. Keep saying route when what we mean is forwarding instructions. So we have to build a route, an end-to-end view, but then we have to tell the individual routers in the network how they forward a packet. What is the packet in, packet out mapping? So distributed algorithms work best when, let's say, they work out the best here to the destination path. So starting from here, I'm going to work out the path towards the destination, and that will tell me what the next hop is. And then that next hop is installed in the local forwarding table. On the other hand, a centralized algorithm is working out the best end-to-end path, and then it has to push the forwarding hops for every router in the network. So it's doing a network programming action. And how do we influence the forwarding? Well, forwarding is essentially a lookup table where we take some fields from the packet, look them up in the table, and find out what to do. The obvious is the destination address lookup. And we apply a little filter to that, a longest match first, so that we can do fine control underneath aggregation. We could also base the lookup on any other information, right? Not just the destination address. And this gives us fine controlled decision-making based on additional semantics carried in the packet. And we call this process semantic routing. Obviously, the algorithm also needs network state. And it's worth noting that a lot of this approach has been pioneered initially with OpenFlow and now with P4 as a way of SDN pushing programming instructions into the forwarders in the network. So, as I said, address-based forwarding is one of the core approaches, and not all addresses are equal. What we've done in the past is set aside some address ranges for special meanings, and a couple of those are anycast and multicast. And the address there is recognized as belonging to a specific set of addresses that are subject to a different forwarding paradigm. And those forwarding instructions could be put into the same forwarding table as is used for normal unicast, or there could be a new forwarding table because additional actions are needed at the same time as forwarding, such as replication. And obviously we have private address spaces as well, and therefore routing and forwarding within a limited domain. And if you see those addresses in other places, they will have other meanings because the addresses are not shared across domain boundaries. And that means we can apply any modification to addressing we want within the domain. So semantic addressing is a phrase that's been kicking around for a little while. And it observes that only the first part of an IPv6 address is actually used for routing and forwarding. And that gives us some additional to play with. And we can vary what those bits are for, and we can carry additional information that maybe is used to influence the routing and forwarding. So I started to collect some use cases and proposals for this, and decided I wanted to limit myself to 20-point font on this slide. So I stopped at this point, but you'll see there are lots of things that are proposed, and some of them are actually done and deployed that use these overloadings, I would say, of the IPv6 address to carry additional information that guides how the forwarding happens. So we can also carry additional semantics in packets using other fields. So we might base this on information not normally used for these routing purposes. Information that's carried in the packet fields already, but isn't usually part of the routing or forwarding decision. And the diffserv fields are a case in point. So you could set yourself up without any further changes and say, I'll forward all packets with type of service red down one link, and all packets with type of service blue down another link, and they could go different ways through the network. And that's sort of how we build multi-topology. We could also put this additional information into existing fields, but giving those fields new meaning, so overloading. So already talked about semantic addressing, but we can repurpose existing fields. And the most often talked about one is the IPv6 flow label, because many people think, hey, there's a field we could use to guide the forwarding decision beyond ECMP. But you can do that in lots of the existing fields, just bearing in mind that when you overload a field, you obviously take away from its current meaning. So the third option is to carry additional information in new fields. And the easiest in IPv6 is to define a new extension header and put in routing information into that header, maybe describing the service that you want, maybe describing the quality of forwarding, and then you can route on that. There are other proposals and things out there, an additional encapsulation that goes somewhere between the IP header and the payload, or new MPLS special purpose labels to carry extra data that can be used for routing. All of this leads you to be able to make advanced forwarding decisions based on things beyond a simple table lookup. So you could do a lookup with all this extra information, a very big index into the table, and make a decision. But you could also make complex decisions almost on the fly, using all of this semantic information, considering the latest state information you have about the network, maybe from OAM, maybe from the routing protocols, and then running an algorithm to decide packet by packet how to forward. And those algorithms could be built into the router, or they could be installed, pushed down through network programming. So this architectural picture was really intended just to say, hey, look, not a lot has changed here, except for the addition of the word semantic in red font in a few places. Of course, this is overly simplistic, but and we need to look more into the architectural implications, but it gives you an idea that we're not totally tearing up the way routing works, but we're adding functionality. So prior art, we started to put together a survey of proposals and protocols and implementations and research that had done semantic routing, and we found a lot. I just listed out 4 here that all happen to begin with the letter S. Scion, segment routing, you probably all know about. Service function chaining, you should know. And semantic addressing, as witnessed in approaches like Lisp and ILNP, where the address space is broken up so that you can do backbone routing and edge routing. I won't go into those, but I do want to talk a lot more about application areas of interest, because we really need our work to be driven by use cases that have applications behind them. So the big buzzword at the moment is network slicing, and that's largely being driven by 5G, but there's some background pressure from emergency service and government traffic And what they want to do is set aside resources in the network for use by traffic from a particular network slice. So customers, users, applications can be routed onto that slice, and then they will know that they're getting a particular quality of service. Some approaches here require the packets to be marked to indicate which slice they belong to. And you can see that that marking provides a type of semantic routing information key for the forwarding. So other use cases that are coming along, there's a lot of talk about augmented reality and multiplayer gaming and the pressures that they put on the network. And I have a grandson who gets exceedingly upset when his jitter, that is to say the latency variation, varies. The games can handle it when it's pretty predictable. They need relatively low latency, but they don't need ultra low latency. But if the jitter varies, then the game varies. Remote surgery, much talked about, something of a niche use case. What they need there is very low jitter and zero packet loss. If you consider that a packet is controlling a laser or a scalpel that is inside somebody's body, you really want that to work well. Lots of recent discussion about smart vehicles and smart cities, how the vehicles communicate with each other, how they need to offload compute resources to local and uncongested computers. It's pretty low bandwidth, but it needs very low latency. And then in many IoT environments, there's scarce resources and they need to be reserved for critical flows. So all of these applications could be expressed in information carried in the packets so that the network would understand how best to direct the packets to achieve the objectives of the applications and the users. And there are lots and lots of proposals. There's an absolute avalanche of them. I've only listed a few here, but you can go out and look at our survey, and every day in the IETF, there seem to be new drafts proposing ways of doing this for specific applications in specific limited domains. I've called out APN, satellite networking with semantic addresses, which sort of surfaced at the recent IETF meeting. And there was a BOF also at IETF 113 on computer-aware networking. And Dirk's going to talk a little later about compute in the network, which is kind of related. And there's work just starting in the MPLS working group about how to put network actions in the label stack to provide instructions to enhance the forwarding decisions. What we see here is something called stovepipes, and we have lots of different solutions being developed and optimized for specific applications and specific network technologies. And each is deployed in what RFC 8799 calls a limited domain, with the intention that they should not interfere with each other or with the rest of the internet. Problem is, these solutions can rarely be used for other purposes, and that makes the whole thing rather expensive, both in terms of development and testing. So we can look at, step back from this and look at the general engineering challenges, things we want to achieve and bring into a common solution. Listed a whole load of these. I thought for a moment I was going to only have the letter M, but I managed to get back to S at the end. Stability at the very bottom, I think, is key. When we play with routing systems, what we need to end up with is a stable system, and it has to not damage the rest of the internet. So briefly, we need to look at the architecture. So I talked about this being done in isolated domains, and when domains are physically separate, you can get away with a lot. You can build your own routing protocols, your own forwarding rules, and pretend that you're isolated from the world. But very quickly, what happens is somebody says, I've got another network that's doing exactly the same thing, using the same protocols, but it's remote. Can we connect together? Can we bridge our domains over an IP network? And then maybe you want special behavior from that IP network. And then maybe this develops into a portion of the internet which is using a specific prefix in the address space to mean this is how we're behaving. So it's not actually physically isolated, but it's logically isolated by those address prefixes. And then I should have made this list the other way up, I think, because you start with your own private domain, and then you gateway either into the internet or you use overlays to reach remote domains. And then you start to find that the function needs to leak out more generally into backbone networks and even into the global internet. So how you build the solution, how you think about the solution depends on the scope that you're trying to deploy into. So risks. Risks is where I got into this whole thinking about semantic routing. And we should think a little bit about why they're important. So obviously the new function we have, we want it to work. We want people to be able to build it and deploy it and extend it. It's no good if it's so complicated that nobody dares touch it. And it would be really nice if it was widely applicable so that our engineering solution can solve many problems. And of course, we really, really don't want to break anything else. What we do in our own private network is one thing, but as soon as we break what's going on elsewhere, we must not risk damaging the internet. So what are the risks? What are some of the big concerns? Well, stability and packet loss. You've probably heard people talking about router thrashing and link flaps. And we don't want to have a routing system that is constantly changing how it sends packets to such an extent that packets can't find their way through. We have to coexist with existing routing systems, either as ships in the night or isolated domains, or if we're really lucky, with seamless interworking. So it just all works. Our new system and old routers will all coexist and happily forward traffic. But really big consideration needs to be what happens if packets escape from our new system into older systems. Will they cause routers to crash? Will they cause unexpected behaviors? Will the packets actually get through, or will they be dropped? And security, okay? Are we introducing new risks or are we actually fixing holes in security? Are we making scalability worse or better? What are we doing to the routing and forwarding table sizes if we're putting in lots of fine granularity lookups? How much routing data needs to be exchanged between routers? And what result does that have on how quickly routers can converge when the network changes? So in effect, what is the impact on the complexity and the fragility of the system? A lot of this semantic routing really still qualifies as research. We're playing around with, could we build this? What would happen? Can we deliver functionality? And routing research needs good research challenges. So firstly, obviously, do we address all of those risks? We need to look at how we characterize the paths. There's a lot of information now to describe the paths that we want and the paths through the network. And a lot of that may change very frequently. So we need to work out how we actually build a data model for our network. We should always look to see whether we can meet the requirements with existing tools. It's fun to be an engineer and invent something new, but it's even cleverer to be an engineer and use what you already have. So can we get away with existing hardware? New hardware is expensive. Do we need new routing protocols, or can we just tweak existing ones? Do we optimize or generalize? Management always gets forgotten and gets left till last, but manageability is part of the complexity of the system. So we need to think about that. And then lastly, and really only lastly, we need to think what needs to be standardized. If this is proprietary or in an isolated domain, then maybe you don't need to standardize it. And my last bugbear, as I started to look at this, was that the research needs to be high quality. It needs to be targeted, so we need to know what problems we're trying to solve and what is the commercial motivation. You won't persuade a router vendor to build something unless they think they can sell it, and you won't persuade a network operator to buy it unless they think they can get revenue out of their network. The research needs to be rigorous. We need to understand how we prove that the risks and challenges are addressed, and we need to test on a range of realistic networks, not just simple linear networks, but big proper networks with real configuration. Ideally, then, our research should also be repeatable. That means making data sets public, maybe making open source code, and making it so that we can reproduce the results. There's nothing quite like an academic survey that says, here's what we did, and believe us. So where does this fit in the IETF? Just wrapping up with this, there's some established solutions already that have homes in the IETF that fit into the bracket of semantic routing. And you can go to Spring and DepNet, SFC, MPLS, IPPM, and everywhere else and see these popping up. Some niche applications have been getting attention in the IETF and IRTF. There are some new proposed solutions popping up. We saw them at IETF 113 in the routing working group and also on the inter-area mailing list. Dirk is just about to talk about some aspects of computing the network and the programmability that goes with it. But currently, there's no overall coordination, no architectural view of how do we pull all the bits of semantic routing together. Can we find a single protocol solution? So how can you work on this? Well, it's the usual IETF behavior. Keep reviewing drafts. Keep writing up your new ideas yourself. Keep doing research and publishing it and presenting it at the IETF meetings, or send it through to me and we'll pop it on our semantic routing wiki. And we have a workshop coming up at SIGCOMM in August that's looking at the future of routing and addressing. So you can look at some of the reference material in the slide sets that will be online, and you can ask questions. And I see that there's a queue already.
Yes, Adrian, thank you. We have a question from Dirk. Maybe I would like to request Dirk to maybe go ahead and ask the question directly, Dirk.
Yes, so there was a question to the computer-aware networking that you mentioned before. And I think the work there is really still quite in the beginning, but I wonder how much semantic information do you see needs to be carried for computer-aware networking, or is it more about enhanced information to do the computer-aware routing decision?
Oh boy, well, the challenge here comes in breaking down the computer-aware networking into its use cases. And I think some of those use cases are quite high level and are really service level functions, because the compute is long term or is on a large data set or is spread over multiple requests. But the other end of that is where there is a small amount of data, maybe even fits in one packet, that needs to be sent somewhere for processing and to cause a response. And there, I think it may be the case that a packet would be marked with its intention, which is, I need to get somewhere quick, and I need a quick computation performed on this data, and then a response sent to me.
Okay. Yep. Thanks.
Thanks, Dirk. Thanks, Adrian. We have one question, Adrian, in the chat. I'll read it out for you. With more data in the packets, each packet would require more CPU resources and probably slow down the packet processing. So what are the approaches to minimize this?
Yeah, that's you can have it high function, fast, and cheap, but never all three. And this is a classic problem. And I think that the data, the challenge is how we represent the data, how we represent the information that we want, so that it can be minimized in the packet and also in the lookup. And diffserv is a good marker for us here, because what we can do is color a packet, and the packet then only has to carry one piece of information, that color. And we can program the forwarder to look up that color and know what to do. Then our complexity is just in the routing and the mapping of the color to the detailed information about what forwarding path we want to generate. But I completely agree with you here, Sumit. It's a challenge.
Thanks, Adrian. Sumit, I have opened up the mic for you in case you would like to have a follow-up question on that.
Yeah, I am good. Thanks a lot for answering it.
Thanks, Sumit. Thanks, Adrian. Okay, we have a question in the Q&A. Let me read it out for you. Any comment on reverse internetwork architecture by John Day, if you have come across it?
I have, and I think it's foundational to all of this discussion. And the question it brings up for me, and I don't have an answer to, is should we totally re-architect the internet? And what are the costs and implications of that? Or should we try for a step-by-step evolution towards what we want to achieve? I know which is more fun, and I also know which is quicker.
Okay. Let's see if there's a follow-up question. I don't see anything at this point. Panelists, if you would like to ask a question, maybe you can raise hand. Okay. I don't see any further questions. So thank you so much, Adrian, for that wonderful presentation. It was great having you with us. Thank you. So moving forward, we will go to our next talk. Let me start sharing the screen to introduce Dirk. Right. So the next presentation will be by Dr. Dirk, and the topic is computation in the network. So Dirk is a chief network architecture researcher at Huawei's Applied Network Technology Laboratory. He has more than 25 years of experience in network architectures, services, and wireless technology, with main contributions in the area of interdomain networking, as well as seamless handovers, physical network overlays, and new service concepts for the operators. Prior to joining Huawei, Dirk was a senior principal engineer at InterDigital Europe, leading the network research team in the London office as the technical lead of the Horizon 2020 Point, Rife, and Flame projects on service-based architectures. He has published more than 85 peer-reviewed papers in international conferences and journals, and holds currently more than 30 international patents in various areas. He was listed among the top 50 industrial IoT innovators in the 2016 RCR wireless list. Thank you so much, Dirk, for joining us. I'll stop sharing the screen. And once I see your screen, I'll confirm.
Thank you. Let me try to share the screen and hopefully it's going to show up.
Yeah, it's coming up. We can see it.
Good, very good. Thank you very much for the invitation. I'm very happy to be here and it's been great so far, so I hope I can continue. I was asked to talk about COIN, computation in the network, which makes it a bit difficult because I'm active in COIN. I'm giving you thoughts, views, hopefully insights. I hope I can fulfill the challenge that was given to me with that. And it's a bit, obviously, as also Adrian mentioned before, more based in the IRTF, so looking more at the research domain and the connection to the ITF. So a bit about myself, in addition to what's said, apart from the 25 years and the working with the various companies, I've always gone back and forth between industry and academia, and that can be seen by working now at Huawei and still being quite active in the IRTF and trying to bring new research into the IETF and into the IETF process as well. A lot of it is really probably coming out of my history and going back and forth between academia and industry. I worked on future internet stuff. Adrian mentioned just before, wouldn't it be nice to reinvent everything? We got a big pile of money, good deal of 12 years ago, both in the US and Europe. Asia came a bit later, but also a lot of clean slate stuff. So I was doing a lot of these things. I was working there, leading actually the first publicly funded project on information-centric networking. If you know that area, that was one of these things about IP is bad, let's just do something better. And it gives you very, very good insights, because it also leads you at some point, if you do more trial-based standards development, to realize what the limitation of that approach is. It's the reason why I wanted to mention those things. So the wandering between those boundaries really questions almost everything, but it also makes you wonder, if things do make sense when you want to deploy them. It gives you good insights. So try to answer the question, what is COIN anyway? A bit difficult because, as I said, I'm not the person who came up with the idea of COIN. Well, it stands for computation in the networks. If you look up the website of the COIN RG, so it seems to be about computation or computing. Question though is, isn't that what we're doing in networks anyway? Maybe it's more than just packet processing. Maybe it's about programming more than just executing instructions. Computing can be both. Obviously, it's about executing instructions, but maybe the programming part could be key. In networks is another piece you pick up. Question there, I think, even after 3 years being active in Coin, I'm still struggling whether network is a horizontal or a vertical aspect. So is within networks, or is it, if you would describe that slightly better, is it on path, right? And how does that relate to edge computing? And the various initiatives you can find in that area. Don't expect very, very clear answers on those questions. I have viewpoints on them, and that's what I'm sharing. So don't take my word as the final one for that. So what are the insights I'm trying to give? First, a bit of an overview of what I know that the IETF is doing on this. So I've been active in the CoinRG before I joined Huawei. First draft in the activities in CoinRG I did about probably 3.5 years ago. The pandemic made me lose the sense of time a little bit. Use cases for Coin I'm going to talk about, and what's being done on computer awareness, as Adrian mentioned before. So it's the CoinRG in the first part. The use case draft in the CoinRG I wanted to look into, so to give you maybe a bit of more of a sense of what Coin is about. Use cases are very often good to look at. And then in the third part to talk about the efforts on computer-aware networking that Adrian also mentioned before already. Once the slides are being sent away, when you see these funny, I put links under some of the aspects. You can easily click on them. So if you download the slides later, I hope the links will be usable. So it leads you to the charter at the moment, for instance. And as I said, this is entirely based on my own view of how I interpret the information that you can find available on Coin. I presented this also recently, or part of this in the CoinRG as a very, very individual view in how I look at Coin. So what are the core concepts? If you read the charter and advise you, in case you haven't done it, I'll go through. That's probably a typical pit stop for anybody who would like to understand what Coin is. You naturally, if you type an IETF in Coin and about, you end up at the charter page. So if you look at this, I already mentioned computer the network is one of these terms that has been written, and it's in the word, right? It doesn't seem to be about active networking. In case that comes to your mind, a recent statement by John Crockett on the list made it at least asserted that compute in the network is not active networking. Interesting discussion point where the differences are. We haven't gotten to that yet. A lot about in the charter on programmability of the data plane, which may result from the compute in the network vision. Again, as I mentioned before, so not only about executing instructions, but maybe also programming them, meaning changing them. Notable here is that it talks about programmability of the data plane. Strangely, not about the programmability of the control plane. Just to keep that maybe in mind. A word that's very often being used is the cloud edge continuum, particularly when you move beyond packet interception, packet processing to the processes that Adrian was talking about in semantic routing, towards computation in general, more than just looking at a packet and deciding where to go with it. Right. Orchestration is being talked about. So you need to orchestrate the research usage within a computer network. If you want to program things or you want to move state around, orchestration is a word that the charter points to. And it talks about decentralization, so move beyond just the data center. And I think there's links to the cloud edge continuum. You can see 2 bullet items up. So these are kind of like buzzwords that I pulled out when I first also read the charter quite some time ago and then revisited it a couple of weeks ago. What are the intended methods? So apart from what is it seem to be about, what are the intended methods? So what is Coin doing really? Again, looked at the Coin charter. It does talk about use case driven requirement analysis. So identifying benefits and as also Adrian pointed out, sometimes looking at use cases may help you understand what it is really you're talking about. They may come from the outside and they come from within the Coin community. I talk about the use cases later a bit more. It talks about research. It's a very prominent word. So new users, new languages, new abstractions, new architectures, new protocol designs,
but in particular to attract the wider community to bring work to COIN. That's a bit of a way that the IRTF is trying to change itself to attract more of the wider research community, to exchange with the community as it is, or also to refresh the community that you can find in the COIN-RG meetings by bringing work to the RG meetings. And if you look at some of the agendas, a lot of those are being shaped by presentations of research work that you can find elsewhere that is being deemed relevant to the discussions in the group. Also to pay obviously attention, it's been the COIN-RG is embedded into a construct, which is the IRTF and the IETF more widely. So what's happening elsewhere in other RGs, but as I mentioned, also sometimes work is being pointed to ongoing working group work, which is in the IETF. That's one of the benefits, of course, to take place within the context of the wider IETF, but it also links to IETF work, not just research group work. The ones that are particularly mentioned are the PRG and the ICNRG, where you see cross-fertilization. As I mentioned, interacting with the IETF, particular with the sense of avoiding proposals that increase the friction. As an example that's been given is privacy and network computing, even though there's very little happening on that at the moment in the COIN-RG, it could be one of the aspects that you would like maybe to address in an interaction with the IETF. There are many vehicles to actually do these things. Internet draft is a relatively common vehicle in the IETF, as you well know, to capture discussions of a group in a draft. Some of those may lead to recorded outcomes in the form of RFCs. Others are just archived discussion materials, papers, public GitHubs. All of those are being used. There's a variety that the COIN-RG has. Actually, at the moment, there's only one so-called adopted internet draft. Most of the other drafts, if they exist, are just drafts. They're being brought. What are the main thrusts? If you look at the charter, you can recognize visions and technologies for computer networking. So we want to look at what is it that we're talking about, but also what are the technologies that are maybe constituting contributing to the vision of computer in the network. That's I put this at the bottom. Being embodied and through distributed computing frameworks, languages that allows me to program the compute in the network. And what I call applicability areas, still a slightly contentious term, it seems to be, but I haven't found a better one. Transport and privacy are explicitly mentioned in the charter. There have been others that have been forming over time. Data discovery was a thrust of work that happened about maybe 2.5 years ago. It's gone a bit silent recently. Routing, not just semantic routing. Routing had been discussed in the COIN-RG before semantic routing came along in some of the drafts, but it's not explicitly at least mentioned in the charter. That's why it animates this way. And there may be other areas, right, that come up, which kind of like utilize the vision that COIN sets out and maybe impacts also the actual applicability area itself. So it's a kind of like a back and forth and informing of, as well as a impacting of the applicability area. I said, this is my understanding. That may have not have given you a very, very good understanding what COIN is. As I said, this is all, most of it is to be read in the charter, and it's meant to be understood possibly in your own way. And hence, this was my view. And that is certainly possibly debatable. What are the use cases that COIN has? Again, you can click on the title, which leads you to the latest version. It's been a growing work. It was initiated in 2 different places. It was an initial draft that was done. Sorry, that's not mentioned here yet. In the history, initial draft that was done by Icons and Klaus Werle on industrial networking, and by myself and my former colleagues from our previous company. And I will have that example later on a bit more. And we joined those efforts into a single use case draft with Marie-José joining and a former colleague of mine, Xavier. We have people from UCL participating. So it has become now quite an effort with a number of authors. The first thing we attempted, even though rather late in the draft, only in the third version we attempted this, is a coin terminology. Not particularly innovative, but we wanted to stick things down so we can name things while we use them throughout the draft. A coin program, so a set of computation that may be requested explicitly by a user to be executed in the network. Picking up on the programmability aspect that I mentioned before. A program instance. So you may execute the same program in different as an instance in different places in the network. It's a currently executing instance of a program. Function, which is a specific computation that could be part of a larger program. So that's we're getting smaller. Coin capability, which is a feature that's enabled through the joint processing of computation and communication resources. So we really want to be really interested in the marriage of both rather than in the single dimension of computation and communication only. We also in the use case talk about coin experiences. These are experiences that are particularly brought about through the utilization of coin capabilities. This is kind of like what the use case draft is trying to capture, those specific coin experiences rather than the one that come along with the larger use case. Programmable network devices is a term finally. We talk about actual components, network devices that are programmable by, for instance, using technologies like P4 or others that allow me to execute the actual programs I'm loading onto them. An execution environment, getting now up again, that is a class of target environments that allows me to execute functions through, for instance, represented through bytecodes or similar things. There has been work, even though the draft expired, on execution environments in Coin until I think the draft expired about 9 months ago, if I remember correctly. A Coin system is then the collection of the various PNDs and their execution environment that allows me to really load distributed programs onto the system and execute them jointly. We use these terms throughout the use case to kind of like pin or point a little bit to the areas where Coin has an involvement and those areas where just traditional aspects of computation come to fruition. So what are the use cases that the use case draft talks about? And we group them into providing new Coin experiences. So again, here the focus on these experiences are coming through Coin. Mobile function offloading is one of the ones that I will talk in a bit more detail in the next few slides. Extended reality, personalized interactive performing arts. So the mobile function offloading, for instance, came from my former team. Extended reality from Marie-José brought this in. This is really a collective exercise, if you will. Personalized interactive arts is work that we're also doing actually together with UCL and the authors, the UCL PIs joined us in the draft to describe new ways of doing interactive performing arts, directly motivated by the pandemic, by the way. We started this about 1.5 years ago, the work with UCL. Supporting new Coin systems is the other group. These may be new systems outside of the maybe existing use industrial network, in-network control, time-sensitive application, industrial safety. This comes out of the initial work that the initial co-authors of the use case draft, Ike and Klaus, were working on, coming from the industrial networking angle. Still very, very focused on industrial networking. Doesn't mean to limit new Coin systems purely on that area. This is where the use cases came from. Improving existing Coin capabilities, content delivery, compute fabric as a fabric, and compute fabric as a service, and virtual network programming are the 3 use cases that are describing the improvement of existing Coin capabilities. And the distributed AI is then looking at new capabilities that may be introduced into a compute in the network fabric through supporting distributed AI problems. What is the lens that we're looking at the use cases? Well, the first we describe, and if you click at the link that that was in the title before, you will see that the use cases are all increasingly similarly described. There are still some variations in the description. If you have that many co-authors, that's inevitable that you have different writing styles, but we're trying to normalize that so that somebody can look through this like a catalog, and the use cases don't look too similar, too different in the description and in the structure. So we try to describe what it actually is that you would experience. what's the character, what characterizes the coin-specific behavior? And again, we put an emphasis there on the coin-specific behavior. What are existing solutions that might come to mind, either ongoing existing work, to realize the actual behavior that's being described? Opportunities, why is this interesting? Both from the perspective of the experience, what is it you're enabling new, or what is the technology that you're maybe utilizing that's particularly interesting here? What are the research groups? This is an IRTF research group. So we are trying to formulate research questions that could drive research guided by those use cases. We're trying to package those, think about research questions you could stick into a thesis. I'm not necessarily saying a PhD thesis. Sometimes the research questions are fine granular enough to maybe boil them down to maybe a master thesis, but they are meant to stimulate people potentially working on those questions in a packaged piece of work, right? Requirements. Well, we do ask the question already. What high-level requirements may there be when you think of solutions and approaches, right? And even though this looks like we're thinking about solutions, we're not doing this in the form of a protocol message format, but more high-level requirements. And it's still being debated how useful that is to do in a research group. But so far, we've kept that part in the use cases. And for us, we're focusing on the research question, the requirements quite a bit as the core part to sharpen the coin scope. The research questions allows us to drive coin work because we can throw these questions at the community and solicit input to those questions. And the requirements, again, when thinking about the solutions, may actually help us to actually look at the areas where we would like to see development happening. An example of these use cases, that's the one reason I'm presenting this, because I know it the best, because it came out of work that I did with one of my former team members, Shatura, and Mike Boniface from Southampton University. So I can describe it the best. You can pick any of the others. It's not that this one's particular special, apart from the fact I know it quite well. It was done as joint work at the previous company I used to work for before joining Huawei in 2019. It coined the word app centers, and the idea here was, you see this later in the slightly more detailed description a bit more, to actually execute applications in distributed data centers, but keeping the perception of a single app running on your mobile device. That was our initial realization of this. And it could run, these data centers could be on sites like hotels, sport venues, but also on individual user devices. We looked even at individual user devices as a micro data center. And if you look at the computing power of today's smartphones, that's not surprising, really. The goal was to showcase. This is actually a use case that was showcased. You see this in a moment. And it was meant to showcase the idea of microservices that roam across devices. And it's, when you see that in reality, it's really quite impressive. It was meant to showcase the marriage of an app in the sense of, well, actually, the actual demonstration was really, it was available in the App Store, right? We released this to the Google Play Store. You could download it. Unfortunately, you needed our infrastructure to run it. So if the infrastructure wasn't there, the app just said, good day, won't do anything. But it was an actual executable app on an Android device. It includes the device-centric parts and the things that are traditionally called network functions. So it was doing both, but it kept that sense of going to a Play Store and installing something. The technology was based, it was meant to showcase the technology that was used, which very often use cases obviously do. And the technology that we were showcasing was path-based forwarding, which allowed it to extremely quickly switch communication relations. I'll come to how quick that really was in the next slide, but also to perform multicast in an ad hoc manner. The demonstration could actually lead to multicast behavior, and that was performed in particularly dynamic. So what was the envisioned behavior? And my apologies, I didn't recreate the actual draft figure, but I think we are all used, hopefully, to ASCII figures. There is one. That's the one in the draft that still exists. And it was an application function offloading example. So in the mobile device, when installing the initial application, the application was designed as a set of microservices. They were not just app modules, which is what you usually do, right? They were actually microservices. DPR stands here for display processing receive. So you have to read it actually the other way around. You first receive something, which is a video frame. You process it, tilting, morphing, mirroring. There were different functions that we implemented. And then finally, you displayed it. Essentially, we implemented a video player, right? But that's just a kind of slightly more complex description of it. It was a set of microservices, which means it had an efficient intra-app communication when everything was local. It looked like a video player. If you just installed it and started it straight away, the video popped up. But it also had an HTTP-based inter-app communication when it was distributed. So the point, of course, was distributing it. And the transition between local and distributed execution was meant to be highly dynamic. So what happened? So you install it as an Android app, as I said. Beyond the local installation, the packet installer, which was a modified packet installer that we implemented, orchestrated the deployment of in-network functions. And you'll see here, it talks about a processing server. The idea being that the processing may be highly complex, even in our case, it wasn't particularly complex, but you could have done some really hardcore GPU stuff, etc., which the mobile may be able to do, but it's very battery hungry. You want to offload that. So the processing server is being orchestrated dynamically as part of the application process. And in the actual demonstration, we said this may be in your hotel. The hotel provides facilities that you may rent, use as part of your visit. And the processing server is that kind of ephemeral microservice that you may be able to install there to outsource the processing, right? The service endpoint can be highly dynamic. So what's happening actually, and this is not shown here as a message flow, but you may imagine this, if it comes from the actual internet server, it comes to the actual application. It may do the processing here, but the processing is now being offloaded to the processing server. So it receives here, it processes at the server, and it displays again here. So the indirection, and what we did, this is, you see the difference because the processing is done much quicker, despite the fact that you're actually bouncing the frame back and forth. The processing is offloading so much that the effect you see is better processing. The processing server is better performing, and communication is not that expensive on a mobile. The mobile can easily transfer these things. The other thing you could also see is that the battery consumption was literally going down. You had to let the demo run for 10 minutes to see the difference, but the processing, the battery consumption was going down because the intensive processing was being pushed off and replaced by communication, which is relatively constant in the battery consumption. The second part you were doing, the display can be bounced off as well. And what you get is display indirection. So if the display is being disabled, it's being bounced to another display, which is purely for instance, a TV. The display indirection could, for instance, be based on gaze or turning. We just used a very simple button. You pressed on the button and the display was indirecting. The indirection speed was done at frame rate. So at every frame you were able to indirect. Obviously, you have to press the button fast enough to do that. But when you press, the next frame was automatically indirected. We were able to show that in the demo. And that was quite impressive to do that. But you could use things like gaze, turning the devices, indirections that allows you to actually throw the display extremely quickly somewhere. And the lack of any latency in that was really the impressive part that we showed. Now there's only one mobile there, but actually not entirely. There's a mobile and a display. You could also, what you could do is you could throw the display down here and take the display back at the same time. So you mirror it actually instead of indirect. And in this case, you would have two receivers, one internet, and actually the network was doing dynamic multicast. It's not IP multicast. I'm saying multicast. I only mention here that it is that we didn't use IP multicast because the dynamic nature made IP multicast unsuitable. So we used path-based forwarding that allowed you to build communication relations, even in a multicast relation, in an ad hoc manner, from one frame to the other. So if you switched off the display, and you could equally do in the demo, you switched off the display and the multicast went away, and there was no communication loss or communication waste that happened. So we implemented what we then later called in-network collective communication. It was demonstrated the first time in 2019 at the Mobile World Congress. That was still my old company. The question is this coin or edge computing? So this was what we were debating when trying to see, do we want to actually keep this in coin? The placement of application level functions in network, we actually use Tasker, and which is part used in Etsimano. We didn't use an actual Etsimano implementation, but a simpler version of it. This is what I would call traditionally edge computing. So it's kind of like more going in the both direction, because the support of highly dynamic indirection and collective communication was relying on in-network functions. It was still packet processing, I do agree, but the packet processing was more than just the normal table lookup based on some routing decision that Adrian was talking about before. So this is the reason why we said this is also coin. It's a mixture of edge computing and coin, and hence the use case survived and is still in the draft. The number of requirements, as I mentioned, we do talk, and these are kind of like the set of, I'm not going to go through them, don't panic. But they were kind of requirements we wrote down on various areas. You see there already routing. It talks about service routing, not semantic routing. You can argue that maybe service routing is a subset, semantic routing. I'll leave that to a different discussion. But routing was part of this. There were forwarding decision requirements, affinity requirements. So if I make a certain selection and because of client or service-specific ephemeral state, I may need to stick with that decision, and how do I do that? Deployment requirements, synchronization. This does not mandate solutions. It just looks from a use case perspective as to what needs to be done by any solution in order to make this use case work. So this is how the requirements are being formulated. You can find this for most, I think there's one or two use cases still missing that don't have requirements, but most of the use cases have these type of requirements as well. I hope this gave you some insight as to what are some of the, and you can read through others. As I said, this is more an application that may give you an idea of how you as a user could benefit from it. The industrial networking ones are quite interesting, even though they are obviously less about end users, but more about machines, talking to control elements and make sure that they are not running berserk in an industrial safety environment, for instance. That's one of the use cases there. Virtual network programming is a 5G use case, which is quite interesting. So they're very varied in a way, ranging from end user centric ones to also network centric ones. A bit about the computer-aware networking that we already heard before. But the question is this is also why I asked the question, is it maybe coin, is it maybe semantic routing, or is it something different? From my perspective, they all relate somehow to each other. There is, in some of the aspects that are done in computer-aware networking, there may be in-network computation and also in-network programmability that may be required depending on your dedicated solution. But it also has to do with, hence my question to Adrian, with additional semantic information you're actually using to make decisions. So that's the reason also for including this into this presentation. The use cases that have been, so maybe as a background, there's a pre-BOF that was organized on the Tuesday of the ITF week. And it was a pre-BOF, which means I hope I position this correctly, because the word pre-BOF is still confusing me somehow, because I only know BOFs. I think it's a non-working group forming BOF. I think that's the official description of a pre-BOF versus a BOF. It was a very interesting event. I participated. Hopefully some of you did as well. And the discussion was around use cases, gaps to existing solutions, and potentially ideas of how to implement some of these things. So I'm going through some of those, and the use cases, they're not all typical internet. But the commonality is they are driven by the need to be flexible when you select an instance. So that means that quite a bit of a driver here is the idea that you have computational capabilities of services residing in different parts of the network. So not just in a single data center where you just direct your request to the data center. The data center uses a data center internal platform like Kubernetes to direct the request to the appropriate microservice instance. That's all invisible to the internet. Now here the problem is really that the service instances may be visible, the various locations of the service instances visible to the network, and hence you need to make a decision of, are you sending it left, right, or middle, right? They're not all, as I mentioned, not all typical internet. Some of the ones could be stateless chunk retrieval. That's a typical internet scenario. Like AR, VR, over-the-top video, software updates, they all pull data pieces from essentially file storages. It's done over HTTP and it all looks very fancy, but that's all it is. It's a file download. It's done today through CDNs, overlay servers, message brokers, various solutions that allow you to do that. The service is stateless, so a decision of where to pull it from may happen for every request. If you would assume the data to be appropriately replicated over 5 different locations, you can pull one chunk of data from one location, the other chunk of data from another one. So the decision could happen for every request, really, which makes that an interesting problem. Maybe a very mundane use case, but it's actually quite interesting to think about. Could you pull this actually collectively, from any of the 5 or a combination of the 5, etc. Industrial networking is another one. So workload-based decision, where the workload may either be stateless again, or require several requests per workload. If you have some ephemeral states, so we also work there with several universities on some ideas of how to cater to the desire of the industrial networking industry to move from the relatively static relations that you have nowadays in OT to a more virtualized cloud-native approach. And then the workload handling in a virtualized environment becomes very much a computer-aware networking problem. Vehicular communication is another one that's been mentioned in the use case draft. So more 6Gs maybe. So communication with a localized edge while you move. So here you have potentially 2 problems. Certainly people are moving. Even if you have short service transactions, people in cars, but it's mainly the cars maybe that communicate. And while doing so, you may want to be so-called handed over to another edge cloud instance, because the one you were previously connected to in order to serve service requests may not be the best one anymore. Not even the shortest one, as Adrian mentioned before, may not be the best one either, because it may be overloaded. If you're standing at a traffic light with a lot of cars, going to the nearest one may not be a good idea. So having some more informed decision of where to go and being served in these type of environments is quite interesting. So what's wrong with existing solutions? I mean, I tagline this with dynamicity kills. So, if you talk about service access here, isn't that an application in layer problem? Sure. I mean, what we do today is we do resolution, of a name to a locator, and it evolves, and I may even employ some sort of load balancing decision into the locator resolution. So if I couple my DNS with a load balancer, I may give you a varied answer to the resolution based on the load of my 5 candidates that have all their 5 IP addresses. But all of that involves additional latency, right? The frequent resolution, that's prohibitive. The other issue with these resolutions is it's usually done once, and then you're being pinned to one server and you stick with that server for quite some time. Why? Well, if you keep doing the resolution, you get signaling overhead, the completion latency get worse. There are also if you use the DNS, you may get anyway a cached response from your client, so it's not helping you to frequently resolve anyway, because the DNS uses a lot of caching, and that's an issue. It involves third parties, and that means it causes path stretch, so it's not optimal. It's inefficient in the network because of that path stretch. We could use routing policies for some of the problems that the use case described, but routing policies, for instance, in EIGRP, they could be used, but they have a very, very frequent signaling. They're not reactive to changes, and they're usually not computer aware, even though EIGRP can do load, but it's relatively basic, and it's mainly load, right? And we encounter a lot of, in particular, edge computing scenarios where load is not the only criteria. Sometimes it's something relatively simple like hardware capabilities that you would like to choose. So you would like to be directed to an edge data center, but you may have hardware requirements for the service instance, for instance, GPU support, and that may need to be addressed in the selection as well. So you don't want to be directed to an edge computing center that doesn't have GPUs. We actually observed this quite a lot when we ran trials in my previous company for some of the for media delivery, AR, VR. A lot of those are very, very dependent on particular hardware dependencies. What about if you use low latency reporting with an input selection? And you could do this at the routing layer, but you could also do this at the application layer. But again, it requires frequent signaling. For instance, of things like a weighted sum of an instance load and latency, and that very, very quickly, and we've also seen this in the above, it's a concern by people on the chat, poses the routing scalability problem. If I dump this into the routing protocol and I do this very frequently, what's going to happen? And Adrian mentioned that before, do I break the routing system? It's not something really that I want. The other thing, and I don't have the material here, would really prolong the discussion quite a bit, but also if you do reporting-based decisions, they select an instance based on a set of signaled metrics. So if you want to change the selection, you obviously have to signal the new selection again, and you get flapping behavior. And you can create very interesting scenarios in which you simply keep flapping between service instances, leading to less utilization of the system because of the flapping behavior, which in the end doesn't help you either. So something we actually looked at, and this is outside of the CAN-BOF, we haven't brought this to CAN itself, is what you want, I partially brought it there, so what you want is a direct data path solution. This is what CAN at the moment is discussing. In the gap analysis that CAN presented, that was presented at the CAN-BOF, the comparison is with so-called off-path solutions, with indirection solutions, and advocating a data path solution, an on-path solution, right? You would like to be computer aware. I think that's the whole point that's in the name, right? And that's very important. And a minimal signaling may be an issue. Again, there are various discussions around how to actually, what metrics and how to do the actual metric and the signaling. But I think a common agreement is that signaling should be minimal. And the question is also, who do you have to signal to? Again, if you put it to a routing protocol, it's being seen by every router, even though you may only need the information at the ingress of the network, but you're still flooding the entire network with it. So the signaling is a real issue as well. What are the key opportunities? Why even wanting to do that? And that is generally better experience. You get improved end user experience, and we've some work that will be published soon in the networking conference. We just received the notice for that, where you improve end user experience because you get faster completion of service transaction. If you have more intelligent decision in the network, that then gives you a better user experience because a faster completion of the transaction in certain scenarios, even in file download, gives you a smoother play out, which is good. People appreciate that. And we can translate that to some of the key use cases. It improves network utilization. Routing to a suitable service instance increases the overall good put. So that's a good thing. You may also, that's a metric that we introduced in evaluating these mechanisms, you may be able to accommodate more users. So if you have a given system, and the simple benchmark there can be a file download. So what happens if I have a file download and the decision is rather infrequent? It's based on an initial load balancing decision. But after that, I'm sticking and how many users can I accommodate with this particular dimensioning of the system versus I make these decisions much more frequent based on, for instance, compute capabilities. So I'm sending requests in proportion to the capabilities of the computational resources executed service instances, and I can accommodate more users. That's a good thing. So it improves network utilization because I do more with the network. And the same reads obviously for the compute utilization, right? If I can accommodate more users with a given set of equipment or deployment rollout, that's a good thing, right? And so both service providers and network providers would like that idea. As I mentioned, what are the efforts? What else? What was done? We had several drafts, including in Coin, right? Scheduling mechanism based on data frame programmability. That's a paper that's being presented, and it wasn't a draft, but a paper that was presented in Coin on how to do this. This was actually using a reporting-based approach. We're still suffering from the need to signal the metric frequently. Already mentioned the CAN pre-BOF that happened, where we had presentations on ETSI-MEC and related efforts in ETSI and ITU, use case and requirement gap analysis with existing solutions, but also already discussing potential on-path solutions that may address some of the issues and realize the use cases. There are a lot of open questions, and the reason from my perspective to do a pre-BOF like this, because this is a non-working group forming one, so it's a relatively initial still, is to also come up with the right questions that still need addressing when moving forward. I teased a few out here, but that I observed, and again, this is obviously very personal, sifting through the chat, which is available in the minutes, by the way, for everybody to look at. One of them is about how to ensure multi-AS operation, that maybe wasn't entirely clear. Is this running over just one network, or is this running over several networks? And that really depends on your use case. You know that question. But on the other hand, if I'm a network operator, I may want to provide the computer-aware capability across several networks, not just my own network, to my customers. So multi-AS may be possible. We also have relatively new discussions with somebody who approached us after the pre-BOF to look into drones. So this is a company that works on drone-based delivery, and multi-AS is an absolute given, right? And they're quite interested in doing computer-aware decisions in connecting to ground stations and to service endpoints in the ground stations, and multi-AS is a given for them to work. Where should it be implemented? Layer 3, maybe implied when using words like routing. Layer 3.5, extension headers. Layer 7, there was a quite lively discussion on the chat around that. How do you handle affinity? And what's the impact of that, right? Computer-aware decisions are all good. But if my service has fairly long-lived transactions, not a video retrieval, there you're good. I mean, that you can pull, but one request from here, the other one from there. You have relatively long-lived transactions. You need to stick with the service instance because of the ephemeral state that's being created. Unless, obviously, you have additional means, and that is something you can be looking into, to have a network-assisted way of scheduling and transferring context from one service instance to the other as a result of when I'm driving along the road, for instance, I make a decision in my vehicular transportation scenario, but my vehicle should be handed off to another service instance because I've traveled already 10 miles. And the fact that I'm still stuck with the service instance from 10 miles away maybe not be a good idea. So I'm being transferred to another service instance that may require the transfer of the state, which is best handled at the application level, most likely, but the network could assist in doing that, and therefore allows you to make to make a computer-aware decision as to what's the best data center to stick you now to for the continuation of your transaction. Security, privacy. What is it you actually want to see or need to see where in the network? Even what does it even mean in the network? Is it a network operator? Is it an overlay provider? Is it the service provider? What's the information you need to see? Do you need service information? Do you need to see metric information? There are quite a lot of questions around that. And it's good to have those questions because they give us, open questions to ask and address in actual work. So what are the key takeaways? Well, the one is computation networks is getting richer, not only as an interest, but also if you look at what networks really do, there are more resources available through virtualization. It's very easy to establish computational resources in networks as a horizontal aspect, but also in various layers of the system if you look at it vertically. The resources are getting richer. The capabilities increase. It's not just very simple operations. We haven't even looked, what we're still looking for are the rich use cases for Coin that are really looking into data fusion and data computation capabilities that the network is doing beyond just simple or extended packet processing. More specialized resources, NPUs, GPUs, whatever PU you want to have, you can stick nowadays into certain networks at least. Not necessarily in all of them. New technologies, as I said, more than just packet processing that is being done in the network. It is getting programmable. That's the whole notion of COIN. So the match action rules to process packets beyond longest prefix match. That's what SDN started off. With P4, the packet has become your oyster. So instead of having a couple of very dedicated header fields as in SDN, you can look into anything you want. You can rummage in the packet and you establish rules over almost any packet content. And that's extremely rich, if you will. There are configuration frameworks that ease programmability, OpenFlow, again, related to SDN, pflow. These are all approaches to make the configuration of these distributed programmable network devices possible. And where it's getting a little bit thinner, also in the work in COIN, is about computation frameworks to actually program things, not just configure them. Like say, hey, I don't particularly care. I want to program something, and it's being automatically distributed at the right places in order to achieve the objective that's being encoded in the program. We've seen an interesting piece of work now comes to mind, even though I say there anything question mark. We've actually seen a piece of work called the P4 flight plan work that was presented in the last COIN meeting in must have been 113 was now 112. No, in the interim was actually presented in February. So quite an interesting piece of work that's really looking at the aspect of programming things rather than just configuring things. It's not just research, but it's also not just engineering either. So that's maybe what's well positioned at the moment in the IRTF. Edge computing has been around for quite some time. Standardization engineering is going on, even deployments. But it's also already sometimes more than just app level. We've done also edge computing demonstrations in our previous work. They were not just application level. So maybe there was an early version of COIN, if you will. Nobody called it COIN. It was still called edge computing. We have efforts in the IETF, like the computational awareness, the CAN work that does more than just table lookup packet processing. If you talk about scheduling incoming requests to different points of the network, it is still packet processing, but probably not just table lookup, right? And maybe things like in-network server scheduling and load balancing, there may be the next frontier of packet processing that just goes beyond what we see today. Semantic routing, as Adrian presented before, outlines packet processing becoming much richer. So what is the information you actually want to operate, for instance, for performing service scheduling? It's been going on in the IETF though for ages, even though nobody called it semantic routing. But the actions may also not just be limited on packet processing. I think that's then really what I see coming after the scheduling load balancing to also do really things on semantic enhancement that is not just focused on packet processing. That obviously that also then moves it away from semantic routing. As Adrian correctly outlined, semantic routing is linked to the eventual processing of packets. And then we obviously have the COIN-RG, and that's probably the reason why we have the COIN-RG, to focus on the research, but also bridge to the engineering. Thank you. I hope I finished roughly in time, I see.
Oh, yes, that's perfectly fine. Thank you so much for the wonderful presentation. We already have one question in the chat from Nalini. Nalini, maybe you want to unmute and put the question directly?
Sure. Yeah, thanks for a great presentation. Can you guys hear me okay?
Yes, Nalini, we can hear you.
Yeah, well, this is a little bit of a political argument within the IETF, and there's different ways of looking at it. But essentially, what would you say is the interaction between the end-to-end principle, which is essentially pushing for quote unquote the network to be a dumb pipe and intelligence to reside at the end resources? It seems like don't get me wrong, I love the work you're doing, and I was very interested in the use cases, but it seems like crossing layers. I mean, are you crossing layers? I guess that's kind of my question.
Well, I'm not. Well, I think these are two different questions. Whether we are crossing layers or we are violating the end-to-end principle. I'm just desperately trying to skim through. We actually cite the end-to-end principle in the transport draft. So there's a draft that talks about the impact of COIN on transport. And don't get me wrong, I'm not married into COIN makes always sense. COIN may also have a lot of issues that we still need to address. But we actually mention it there, so you can probably read up the correct quote of the end-to-end principle in there. Now, this is the wrong paper I got here, unfortunately. But the end-to-end principle actually does not necessarily, I don't entirely agree with the articulation of the end-to-end principle as you describe it, and it's how it's very, very often being described. And that should act like a big, fat, dumb digital pipe. That's not what the end-to-end principle says. That's only the first part of what everybody cites. But the second part of the very, very paragraph, and later when I look in a bit more detail, I can send you the actual part of the original paper, does talk about the trusted execution of functions on behalf of the end-to-end application in the network. Now, the key obviously is that this function that may be executed in the network, so the end-to-end principle paper essentially talks about COIN, if you will, without calling it COIN. But key is that what happens on behalf of the application should be known to the application. So there are clearly parts of in-network processing that violate that, because I'm doing it opaquely and the application has no idea. You look at that formulation in the paper and you would argue, yes, you're violating this because you're doing something and I have no idea about it, right? And you're right, I'm pushing something in and it comes out on the other side and I have no idea why it changed. But if you look at how I try to describe COIN as a way to program the functionality, mainly from the perspective of me not just having a program at the ends of the communication, but across the entire network, I argue, and this is what we are saying in the transport draft, that the end-to-end principle still holds. As long as you assure that what you're doing in the network is done not only with my knowledge, but on my behalf, and I have the control over to say, hey, I want to do data fusion, as an example. I want you to do this because I programmed my distributed program so smartly that I know that it should be done exactly at that point in the network. And I'm instructing you to do that. And I'm putting a program or a small little mini program of my big program at that point in the network to do this. From my understanding of the end-to-end paper, this does not violate the end-to-end principle. What would violate it is me coming, or the network operator coming and said, why are you doing this nonsense? Let me just put a data fusion function there. I'm doing a better job than you do. Now that's a bad part. That shouldn't happen.
Yeah, that's a great answer. And let me back, this is in some ways, I agree. There's been other side conversations saying that that's not exactly what the end-to-end principle says. And I totally agree with what you're saying. I think if you're doing it on behalf, but I'm going to watch this space closely. But I'm going to tell you that the quote that I gave, which was actually, I believe, incorrect. I have been quoted that particular thing by leadership at the IETF, and so I will watch with great interest your corrections. Thank you so much.
No, I agree. There's a lot of misinterpretation. It irks me and annoys me that not only leaders at Standardization Forum, but in particular political leaders being also savvy about the end-to-end principle, never having read the actual bloody paper, actually quote exactly the same that you're saying. And I'm sitting there, I had an argument with an EU regulator about this, and I ended this with an angry statement: read the bloody paper before you cite this back to me. Right? And so this is the annoying part. But the point is, of course, and this is similar to, when I do traffic differentiation, and again, you can have two ways of doing it. And one is the one that immediately sets red flags, but a lot of people, including myself, if they have this really, really what they believe are smart operators sitting in the middle doing stuff because they believe it's just better for me. And I have no control over it. And it's quite clear, and also even by looking over the end-to-end paper, that is not in line with the end-to-end argument. But as I said, if I have the control over, and like I said, I want to have this differentiated treatment of the packet in the middle, and I have the full control over the deployment of that function and the knowledge of what the function does, then my reading of the end-to-end paper says that is absolutely okay. It's the control that is so important, not the actual processing.
Or not maybe control, or actually, or even like my consent for you to do that. And I totally agree. Thank you so much.
Thank you. Oh, that was a great question. I kind of expected it a little bit, because that's also the reason why we put it in the transport draft.
Right. Thanks, Nalini, and thanks, Dirk, for that wonderful discussion. We have touched the time exactly, so we are perfectly on time. Thank you so much, both of you.
Thank you. Thanks for having me.
Yeah. So let me quickly share the screen. So first of all, I would like to thank all our speakers for being with us today, and all the panelists also who have been attending this session. Thank you so much for being a part of Connections 2022. And all of those members who are attendees who are new to IIESOC and INTC, we have put up an information in the chat box, which is also visible in this particular slide. You can become the member of both the organizations through the respective links that are provided here. And there are other links also for joining mailing list or WhatsApp group, or following us or catching with us up on LinkedIn or Twitter. I will not forget to thank our sponsors, the Cisco Internet Society, APNIC Foundation, and Juniper Networks. Once again, thank you very much for generously supporting this event. Tomorrow, we have an IoT track. We have excellent set of speakers lined up tomorrow. And also we have a panel discussion. So we look forward to have you all tomorrow with us for this IoT track. Thank you so much for being here today. Bye-bye.
Thank you. Bye.